Hello everyone, welcome to my channel. My name is Mohit and in this video we will study why do we need Adam optimizer. So let's get started. So in machine learning, the main goal is to minimize a loss function, okay, which is a function of parameters like theta. So at each training step t, we compute a noisy gradient from let's say a mini batch, right? So you can say the gradient is given by del theta L theta at a time t. Okay, so this is what we do. So in plain SGD, which is stochastic gradient descent, right? So in plain SGD, it updates every parameter with the same step size. Okay, so let's say we have this loss function. Okay, this is theta, this is loss. So all the parameters are updated with the same step size. Okay, and generally it always react to noisy signal. Okay, so this loss does not decrease uniformly to get the optimal value of theta, but instead due to some noise in the data it follows this path, something like this. Okay, so this issue is fixed by Adam. Okay, so I mean the main issue with this particular approach is that it can take lot of training steps but still not be able to reach at the optimal value. So how does Adam deals with this problem? So basically it try to include two running averages. Okay, first is the first moment. Okay, so it tracks the smoothed gradient descent. Okay, like it is given as mt at particular time t beta 1 mt minus 1 plus 1 minus beta 1 gt. So gt is the gradient and mt minus 1 is the previous value of the first moment and beta 1 is some hyperparameter. Okay, next it also takes into account the second moment, which is given as vt equal to beta 2 v t minus 1 plus 1 minus beta 2 gt square. Okay, so if let's say we have beta 1 equal to zero 0.9, which is a hyperparameter, so it means that your m1 would be zero 0.9 times mt minus 1 plus 1 minus 0.9 times gt. Okay, so mt is 90% dependent on the previous value and only 10%, it's zero 0.1, so only 10% depends on the uh, gradient. Okay, so it due to this technique, the random noise is generally cancelled out, which comes in the picture because of this gt. Okay, and similarly, if for the second moment case we have beta 2 In general it is 0.999. So Vt is 0.999 Vt minus 1 plus 1 minus 0.999 Gt square. Okay. So this Vt now builds a very strong memory or very long range memory of how these large gradients have been for each parameter. Okay. That is the main task of this particular Vt parameter. So it takes a note of that how gradients are moving in the past iterations. But now if let's say we start with m0 equal to 0 and v0 equal to 0, so the early estimates that we will get are heavily pulled towards 0. Okay, so let's see how. So at t equal to 1, okay, so m1 will be 1 minus 0.9 g1 because this part is 0. Okay, the previous value is 0. So it is how much? It is zero point 0.1 times g1. Now in the first step it is underestimating the gradient by 10x because it is zero point 0.1 times g1. Okay, so in order to fix this issue we generally use a redefined parameters, okay, for both of these moments like this. So we define m1 hat equal to or mt hat equal to mt divided by 1 minus beta 1 to the power t, and secondly vt hat which is equal to vt divided by 1 minus beta 2 to the power t. Okay, but this correction does not affects all the iterations. So basically at t equal to 1, what we are trying to do, we are dividing it by this factor, right? 1 minus beta t, beta 1 to the power t. So t is 1 and it is nothing but 1 minus zero point 0.9, and what is our m1? In this case it is 0.1 g. So it is, so this implies mt hat equal to 0.1 g divided by 0.1, so it cancels out and we have g. Okay, and if you see at t approaches to infinity or for a very large t, beta is lesser than 1, both beta 1 and beta 2 are lesser than 1. So this correction ultimately approaches to mt and vt. Okay, because beta 1 to the power infinity will approach towards 0, and similarly beta 2 to the power infinity will approach to 0, and the denominator factor 1 minus beta 1 t or 1 minus beta 2 t are both will be equal to 1 only. Okay, so the next step is how we can update our parameters based upon these two moments. So the parameters theta at an upcoming time step t plus 1 is equal to theta t minus some learning rate multiplied by first moment divided by the second moment under root plus epsilon. Okay, so this is our update rule, right? And the effective learning rate per parameter is, so eta at time t for a particular parameter j is equal to eta multiplied by 1 by root vt j plus epsilon, right? So it is nothing but this this term, okay? This we are calling as a eta j, as an effective learning parameter. So here we can notice one thing, that when vt hat is large, okay, it is large, so it means this quantity is large, and if this quantity is large, your eta t will reduce, okay? So this implies eta t is small, okay? So it means the learning rate is small, okay? So now it will take a smaller steps, so this implies smaller steps or more careful steps, okay? On the other hand, if vt hat is small, it implies the learning rate of that particular parameter to be large, okay? So if learning rate it is large, so it means it will take a big steps, okay? And here epsilon is roughly equal to 10 to the power minus 8, okay? This is a general value, so we include this to prevent division by 0, okay? So in case if vt hat is very close to 0, it will prevent it of becoming 0, and prevent it the update rule by exploding the parametric values, okay? So I hope you like this video. Thanks for watching.